Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 8 on inequalities. All right, so much of algebra is concerned with equality, right? Well, whether it's, just trying to figure out whether one expression is equal to another expression for a particular value of x, or whether it's an algebraic technique to find the values of x that make one expression equal to another expression. But we also want to know when one quantity is larger than another quantity or when one quantity is smaller than another quantity. And those are called inequalities. And you've dealt with them obviously throughout the years. Today we're going to have a little bit of a warm-up lesson on them, and then in the following few lessons we're going to start to learn how to solve inequalities and things like that. So let's jump right into them. All right, the truth values of inequalities. Just like equations can be true or false, so can inequalities, which are simply statements about whether one quantity is larger or smaller than another. All right, so let's take a look at exercise number 1 and try to figure out some true-false statements. Here we go. For each inequality, state whether it is true or false. Now, one thing is definitely important at this point. You are in Algebra 1. So when you look at this statement, right, you have to immediately read that as 7 is greater than 3. All right, if you're still a little bit confused about the direction of that, thing that kind of looks like an angle symbol or whatever, if you have to use the crocodile as eating the larger number, I don't know what you have to use, right? For me, right, there's only really one symbol. Now there's technically two. There's a greater than symbol and a less than symbol. But the idea is the thing that's on the pointy side is supposed to be the smaller thing, and the thing on the open side is supposed to be the larger thing. So this should be read as 7 is greater than 3. And of course, we know that that is true, right? 7 is in fact greater than 3. Likewise, letter B, which says 0 is less than 10, that is also easy enough to say, 0 is less than 10? Sure, yeah, that's true. If I have $0, I certainly have less than my friend who has $10. So that's also true. Okay. Now, our first two were true, but an inequality, just like an equality or equation, right, an inequality could be false. For instance, in letter C, we have the inequality 9 is greater than 12. Well, 9 is certainly not greater than 12. If we had 9 people in one room and 12 people in another room, right, then there would be more people in the room with 12 than with 9. So this is false. Now, the one final consideration when it comes to sort of reading these things is when we not only have an inequality symbol, but a little line underneath it. Okay? And what you've learned in the past is that that's really a compound inequality that says 4 is less than or equal to 4. So if either one of those conditions hold, if either 4 is less than 4, which it's not, a number is never less than or greater than itself, or 4 is equal to 4, which it is, right? If either one of them are true, then overall we say it's true. So when I say 4 is less than or equal to 4, that is true. Okay, so these should be easy enough. What I'd like you to do is pause the video now and give me a true or false on the remaining 4 of them. All right, numbers can be big, numbers can be small, numbers can be whatever. Letter E says 2 is greater than or equal to 7. Well, 2 is not greater than 7, and 2 is not equal to 7. Since both of those are false, my answer here is false. No question that we should also be able to evaluate decimals, right? 3.5 is less than or equal to 4.2. Well, 3.5 is certainly not equal to 4.2, but it is less than 4.2, right? So that's true. All right, letter G, 256 is greater than 312. Well, 256 is not greater than 312, so that's false. And finally, we should be able to deal with large numbers or larger numbers. 1,978 is less than or equal to 2,042. It's certainly not equal to 2,042, but it is less than 2,042. So that is true. So I'm hopeful that anytime you're comparing two positive numbers, okay, you can use common sense to understand whether that comparison is true or false. Absolutely critical. Even if you've got decimals or fractions or whatever, you should be able to say that is a larger number than that. Where it gets tricky is when negatives are involved. All right? So judging inequalities with negatives. For many students, judging the truth of inequality statements when negative numbers are involved, that can be challenging. So let's look at a situation that shows the challenge. Exercise number 2. Consider the statement -8 is less than 4. Do you think this is true or false? Why? Which is the correct truth value and why? Okay, so -8 is less than 4. Well, what I'd like you to do is pause the video, and write down whether you think this is true or false, and you've certainly been exposed to this issue before in middle school. Write down whether you think it's true or false, and tell me why. All right, pause the video now. All right, well look, in the final analysis, the answer is true. Okay, -8 is less than 4. Now, what did you say? Well, I don't know, but there's a variety of things that people might remember. Some people might remember any negative number is less than any positive number. Some people might try to use kind of a real-world analogy, like if the temperature outside was -8 degrees, this is only for people who live in northern climates. Those of you in Southern California probably don't even know what I'm talking about. But, you know, if you're living in a climate, right, that's cold, okay, and you have a temperature that's -8, and you have a temperature that's 4 degrees, well, which one's warmer? You know, which one's a greater temperature? Well, the one that is 4 degrees. In fact, it's 12 degrees greater than the one that's -8, all right? So some people will say that. Ultimately speaking though, right, it's true because -8 lies to the left of 4 on a number line. So let's talk about that a little bit. Let's talk about how we can judge, you know, whether numbers are greater than or less than by thinking graphically, all right? So comparing two numbers with an inequality. If we compare any two numbers, let's call them A and B so that we don't get wrapped up in whether they're positive or negative or anything like that, then A is greater than B is true if A lies to the right of B on a standard horizontal number line, or if the number line was turned vertically, A lies above B on the number line. So it's simply an issue of kind of thinking about where they lie. So if I had some number line like this, okay, with absolutely nothing labeled, right? I don't know whether these are negatives, positives, or some of both, then I could say that A is greater than B, or I could say that B is less than A. Those are the same statements. A is greater than B because A lies to the right of B on the number line. That's it. And what's cool is I can keep kind of like showing you this, right? So like if we had two just positive numbers, like let's say B is 6 and A is 14, well, 14 is greater than 6. On the other hand, if I kind of shifted it down a little bit, right, and let's say A was 4 and B was -4, I could say 4 is greater than -4. And even maybe the most confusing one of all, let's say the two numbers are both negative, right? So I've got a -6 here and a -14 here. Well, -6 is greater than -14 because -6 lies to the right of -14 on the number line. In every single case, all I have to really think about is if I plotted these numbers on a number line, where would they lie relative to one another? And the one that lies to the right of the other one is the larger number. Let's see if we can use that idea to compare some numbers, right? So exercise number 3. Give the truth values for each of the following statements. Draw a number line to support your work. All right, so for instance, letter A, 3 is greater than negative 4. If I thought about that on a number line, right, if I actually kind of sketched out a little number line, right, with maybe 0, 1, 2, 3, right, here would be my 3, 1, 2, 3, 4. Here would be my negative 4. 3 lies to the right of negative 4, so I can say that's true, right? Even though 3 is a smaller sized number than negative 4, that's what we call absolute value, even though 3 is a smaller sized number, we say 3 is greater than negative 4 because it lies to the right of it. All right, what I'd like you to do is do the same thing for letter B and letter C, figure out whether they're true or false, and sketch just a little number line. That should be easy enough. Pause the video now. All right, well, negative 5 is greater than negative 3, letter B. That one is probably, for me, the trickiest because there's this gut instinct to say, yeah, negative 5 is greater than negative 3, but it's not, right? Because again, if I kind of sketched a little number line, let me put 0 right here. This would be negative 1, negative 2, negative 3, negative 4, and negative 5, right? This is false because negative 3 lies to the right of negative 5. Negative 3 is the larger number. It lies to the right of negative 5. Now finally, letter C, 0 is greater than negative 6. Boy, that also seems like it should be false, right? It seems like 0 should be the smallest number possible. But actually the smallest number possible is negative infinity, right? So it's like way out to the left, all right? So this is actually a true statement because again, if I drew a number line, right, if 0 was here, 1, 2, 3, 4, 5, 6, negative 6 would be here, and 0 is definitely bigger than negative 6. In fact, it's 6 units bigger, right? It's all about like how far to the right one number lies compared to the other number. Okay, so we have to be able to look at any two numbers, positives, negatives, or a mixture, and even 0 thrown into that mix, right, like in letter C, and we need to be able to judge whether or not one number is greater than another. And here's why, right? Determining the truth value when variables are involved. We can find the truth value of an inequality that involves one or more variables if we know the values of the variables, all right? So very similar to what we did when we were determining truth values of equations, we're now going to determine truth values of inequations or inequalities by simply putting in values of variables if we're given. So let's take a look at exercise number 4. Given the inequality 3 times the quantity x minus 2 is greater than or equal to 2x plus 1, determine if it is true or false for the following values of x. All right, so this is again identical to what we did with equations. The only difference is now we have to judge the truth value of the inequality versus the equality. So let's do letter A together. All right, x equals 10. Let's see, I'm going to throw the 10 into my inequality. Nothing changes in terms of order of operations. I'm going to have 3 times 8 is greater than or equal to 20 plus 1. 3 times 8 is 24, is greater than or equal to 21, and that is certainly true. 24 is greater than 21, so yes. What I'd like you to do now is pause the video and do all 3 of the remaining ones. You're going to be substituting them into the same inequality and just determining whether they make that inequality true or false. All right, let's go through them. X equals 5. Let's take a look. So I have 3 times 5 minus 2 is greater than or equal to 2 times 5 plus 1. That's going to be 3 times 3 is greater than or equal to 10 plus 1. 3 times 3 is 9, so that's going to be 9 is greater than or equal to 11. 9 is not greater than 11. 9 is not equal to 11, and therefore false. All right. Let's take a look at x equals 1. Oops, okay. So I'll bring that board up in just a second. 3 times 1 minus 2 is greater than or equal to 2 times 1 plus 1. Let me extend my page a little bit. 1 minus 2, be careful there, is negative 1. 2 times 1 is 2 plus 1. 3 times negative 1 is negative 3. Negative 3 is greater than or equal to 3? Nope, right? Negative 3 lies to the left of positive 3, so that's false. And let's go ahead and do x equals 7 right away. We'll have 3 times 7 minus 2 is greater than or equal to 2 times 7 plus 1. That's 3 times 5 is greater than or equal to 14 plus 1. 15 is greater than or equal to 15. All right, let's talk about this for a moment. Again, it's absolutely critical. If I just had 15 is greater than 15, the answer would be false. No number is greater than or less than itself. But 15 is greater than or equal to 15, that's true, right? And it would be like if I walked up to you and said, look, I'm either a professional basketball player or a math teacher. Is that a true statement? The answer would be, well, sure it is, because I'm a math teacher. I'm not a professional basketball player. You know, on the other hand, if I walked up to you and said, hey, look, I'm either a professional basketball player or a professional lacrosse player, you know, you would have to say to me, well, that's false, because you're neither a professional basketball player or a professional lacrosse player. All right, I've never actually even played lacrosse, but, you know, I had to come up with another sport. So this thing is true because one of those two things is true, the fact that 15 is equal to 15. So very, very important that you understand how to interpret that greater than or equal to. All right. Let's do this one more time, but where we have a variety of inequalities, right? Unlike most equalities, most inequalities have an infinite number of values that will make them true. So most equations, right, will have 1, 2, 3, values that make them true. We did see a few lessons back, we did see some equations where all numbers made them true, okay? But that's the rare case, that's the outlier. Inequalities, though, almost always have an infinite number of values that make them true. So let's just go through and see if we can determine for any given inequality whether a particular value of x makes it true or false. Let's take a look at exercise number 5. For each of the following inequalities, determine if it is true or false for the given value of the replacement variable. That's just whatever, the value of x, the value of n, whatever. Show the substitutions and calculations that lead to your conclusions. All right, this is really no different than the problem we just did, except the things can, look a little bit uglier. Let's do the first one together, and then I'll kind of turn you loose to do the other 3 challenging ones on your own. Let's take a look at letter A. I just want to know whether x equals 1 is the solution to this inequality, so I'm going to, or makes this inequality true, I apologize. Right, so I'm just going to put 1 in there. I've got 2 times 1, which is 2. Whoops, how about a plus there, not a t? 2 plus 4 is greater than 4 minus 1. 6 is greater than 3, and that is definitely true. All right, great. Simple enough. What I would like you to do now is do B, C, and D. Be careful, remember your order of operations, and see if those values of x make each of those inequalities true or false. All right, let's work them. Here we go. In letter B, we've got negative 3 times negative 3 plus 5 is greater than or equal to negative 3 plus 7, all divided by 2. All right, we just got to be careful here. Negative 3 times positive 2 is greater than or equal to 4 divided by 2. Negative 3 times 2 is negative 6 is greater than or equal to 2. And that is most certainly false, right? Negative 6 lies to the left of positive 2 on a number line, so that's false. Okay, let's take a look at one that's got a little x squared in it. Been a bit since we've seen something like this, but same idea. Negative 2 substituted into this inequality. Ooh. Take some space just to substitute it in. Negative 2 squared, be careful there. Negative 2 times negative 2 is positive 4. Negative 10 times negative 2 is positive 20. Plus 1 is less than 20 plus negative 10, right? 4 plus 20 plus 1 is 25, less than 10, and I'm pretty sure that is false. Okay, that one's easy to judge. 25 is less than 10. All right, let's take a look at letter D. Here we go. Final one. So we've got 2 times 5 minus 5 plus 1, all divided by 3, is less than or equal to 5 minus 2 divided by 9. All right, in the numerator of that first fraction, 2 times 0 plus 1 divided by 3 is less than or equal to 3 divided by 9. 2 times 0 is 0. 0 plus 1 is 1. So that left-hand side just becomes 1/3. And that right-hand side, 3 divided by 9, can be reduced by dividing both numerator and denominator by 3. And I get 1/3 is less than or equal to 1/3. And that, I almost wrote down, was false, but is in fact true. That would have been really bad if I said that one was false, because 1/3 is most certainly equal to 1/3. All right, so again, this is simple enough, right? We should be able to take any value of x, substitute it into an inequality, and find out if it makes that inequality true or false. You may still struggle a little bit with reading the inequalities. You know, is that a greater than symbol, a less than symbol? But that is something that is absolutely critical to have at this point in your mathematical career. So really buckle down, make sure that you're reading these things out loud. When you see something like this, I want you to be saying to yourself, 25 is less than 10, which is false, clearly. All right, let's wrap this up. So today, we're kind of laying the basis for the next few lessons, which are all going to be about inequalities, solving inequalities, modeling with inequalities. But at the end of the day, right, we've got to be able to read inequality symbols, and we've got to be able to compare two numbers that are being compared with an inequality symbol. We need to be able to look and say, sure, -8 is less than +2, right? We have to be able to say that when we're judging the truth value of an inequality. So we'll get a lot more practice on this in the coming few lessons. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.